Hello, everyone. My name is Isabelle Kuhlmann, and today I'll present some joint work with Matthias Thimm. And yeah, like you already said, the paper is called Algorithms for Inconsistency Measurement using Antiset Programming. So a major challenge in artificial intelligence, especially when we're looking at real-world data, is that contradictions, also called inconsistencies, in that information that we're given are basically unavoidable. So for example, you can think of a weather forecast system that you're implementing and you're getting these forecasts from different sources. Then maybe one source says, well, tomorrow it's going to rain, and the next one's going to say tomorrow the sun will shine. So that there's obviously a contradiction. And the big question now is, how do we deal with such inconsistent information? In the field of inconsistency measurement, we basically have an analytical perspective on how to deal with such inconsistent data. Essentially, the goal is that we can assign a numerical value to an inconsistent knowledge base. There's a great variety of different measures that have been proposed in the literature. However, only very few works are of algorithmic nature. So essentially, only very few works take into consideration whether their measures that they're proposing are actually practically feasible. And that is an important question because most inconsistency measures are complexity-wise quite hard. So obviously, there's a need for more practically feasible methods, and that's also the goal and the contribution of the work I'm presenting today. So what we did is we developed a set of algorithms based on reductions to Antiset programming, or short ASP. And we applied this to the contention inconsistency measure, to the forgetting-based inconsistency measure, and the hitting set inconsistency measure. All three of these measures are complexity-wise on the first level of the polynomial hierarchy. There are also other measures that are complexity-wise even harder. So this is one reason why we decided on these three measures. Someone raised a hand, I saw. Florence, you raised a hand?
Sorry, it was a
okay, sorry. I thought you might have a question. Okay, so I'll go on. So the structure of my talk is going to be as follows. First, I'm going to go over some preliminaries. More specifically, I'm going to talk about inconsistency measurement in general a little bit, and then I'll present the three different inconsistency measures that we work with. Afterwards, I will talk about how we can actually use Antiset programming to measure inconsistency. And also one quite large part of our work was an extensive evaluation, so I will also present some results. And finally, I'll give a short conclusion. All right, so let's start with some preliminaries. First of all, inconsistency measurement. Well, what's an inconsistency measure? It's simply a function that maps a knowledge base to a numerical value. And what this value is supposed to express is that that higher value indicates a more severe inconsistency than a lower one. And also, we need to consider that the value 0 is supposed to reserve for consistent knowledge bases. So 0 means that there is no inconsistency. So a bit more formally, we can say that an inconsistency measure I is a function that maps, like I said, a knowledge base to a non-negative real number. And this function needs to satisfy that it outputs 0 if the knowledge base that's given is consistent. All right, so the first inconsistency measure that I would like to present is the contention inconsistency measure. And this is based on Priest's three-valued logic. In this logic, we don't just have the two classical truth values, true and false, but we also have a third truth value, which indicates paradoxical or both true and false. And it's denoted as B in the following. In this logic, we also have interpretations, and a three-valued interpretation is a model if it assigns either true or both to each formula in a given knowledge base. So the intuition behind the inconsistency measure now is that it describes the minimum number of atoms in the given knowledge base that need to be assigned both in order to keep the knowledge base consistent in three-valued logic. I think this might become a bit more clearer if we look at an example. So let's consider this knowledge base K1 here. It consists of 3 formulas, A and B, B or C, and not A. And now we can clearly see that there's a conflict between the first and the third formula because, well, A and B cannot be true while not A is also true in classical logic. Because if we assign A the truth value true, well, then this could still be true, but then this is definitely false and vice versa. So, but now we can think of a 3-valued interpretation, which actually makes this consistent. So if we assign A the truth value B and the other one, the other 2 atoms, the truth value true, then this evaluates to B, this evaluates to true, and this evaluates to B as well. So we end up with a model of our knowledge base. And yeah, like I said, we can also see that we need to assign at least A the truth value B. So we need at least 1 atom with the truth value B. So intuitionally, our inconsistency value for this knowledge base in the with respect to the contention inconsistency measure is 1. Next, the forgetting-based inconsistency measure. The idea behind this is actually a bit similar to the contention inconsistency measure, but here we don't look at atoms as a whole, but we look at atom occurrences. So the forgetting-based inconsistency measure basically describes how many atom occurrences in the knowledge base have to be forgotten in order to recover consistency in the knowledge base. Forgetting here means that we replace an atom occurrence by either top or bottom. And to achieve this, we need to differentiate between the different occurrences of each atom. And to do this, we assign a label to each atom. Again, let's look at the knowledge base we saw before. So we have the same formulas again, and now we label each atom occurrence. So for example, if we look at each occurrence of the atom A, here's 1, so this one gets the label 1. And here's the second occurrence of A, so it gets the label 2, as you can see here. And the same for B, so this is the first B, so it gets a 1. This is the second B, so it gets a 2. And there's only 1 C, so it gets a 1. And now, once again, we can see, okay, so how many of these atoms do we have to forget? Well, we can forget either this first atom occurrence of A or the second occurrence of A, doesn't matter which one. And therefore, again, the inconsistency value is 1 for this knowledge base. Finally, the hitting set inconsistency measure. Now, this is based on a slightly different idea, because here we're looking for the minimal number of interpretations required to satisfy all formulas in a given knowledge base, subtracted by 1. We need to subtract 1 because if we only require one interpretation, then this is a model and the knowledge base is consistent. But we want the value 0 for consistent knowledge bases, so we need to subtract 1. Also, we need to consider that it's possible that there are contradictory formulas in our knowledge base. In this case, we cannot find any interpretation, at least not in classical logic, which satisfies this. So in this case, we just say that the inconsistency value is infinity. Again, we can look at our example, and we can easily see that, well, we can easily come up with 2 different interpretations to satisfy all 3 formulas. For example, we can have a first interpretation I1, which assigns true to all 3 atoms. So this would satisfy the first and the second formula. And then we can have a second interpretation, which assigns false to all 3 atoms. And this would satisfy only the third formula. But still, now we satisfied all formulas. We can see that we required at least 2 interpretations. So the inconsistency value is 2 minus 1 equals 1. All right, now just a brief overview on Antiset programming. I assume a lot of you are familiar with Antiset programming anyway, but I'll go over it anyway. So Antiset programming, or short ASP, is a declarative programming paradigm, and it's targeted at difficult search problems. So declarative means that instead of modeling instructions on how to solve a problem, you model a representation of the problem itself. So this problem is then represented in a logical format, and the models of this representation describe the solution of the original problem. And these models are also called antisets. In Antiset programming, we have so-called extended logic programs. The difference to a normal logic program, like a logic program, you know, from Prolog or something like that, is that you have two different kinds of negation. So you do not just have the negation as failure, but you also have the classical negation that you can work with. And such an extended logic program consists of rules of this form here. And essentially on the left, you have the head of the rule, and on the right, you have the body of the rule. And all of these variables, so h, a1 to an, and b1 to bm are literals. We can also have rules with an empty body, and those are called effect. And we can also have rules with an empty head, which are called constraints. Furthermore, ASP offers the option to express cost functions involving minimization and or maximization in order to solve optimization problems. And these optimized statements are actually quite useful. We only use a very specific kind of them. We use a specific type of minimized statements in our work, where we basically just use something like this. We have this minimized statement, and then we have a set of literals. And what this minimized statement does, it tries to include as few as possible of these literals. So the ASP solver is instructed to include only a minimal number of these literals in the Antiset. Just a side note here, normally you can also add priorities and weights to such optimization statements, but in our case, we don't need all of that. We basically just want to minimize the number of literals. All right, so how did we use this to compute inconsistency degrees? Well, at first I have to say that, of course, each of the inconsistency measures I presented have their own properties and specifics, which have to be considered individually. However, there are also some aspects which all of our proposed ASP encodings have in common. So the basic building blocks of our ASP programs that we came up with, our ASP encodings, are basically of this form. We have these ASP atoms, and they're of the form E phi t, where phi is a formula or a subformula or an atom, and t is a truth value. So what this represents is that, for example, if we have E phi f, then it means that the evaluation of phi to the truth value f is, if this is included in the Antiset, then well, it means that this is true basically. But I'll give you an example in a little bit, and I think then it becomes more clear. All right. Next, what all of our encodings have in common is something we called unique atom evaluation. And this just means that an atom cannot have multiple truth values at the same time. So for example, if we have E phi t and E phi f, then they should not both be included in any Antiset, because yeah, this doesn't make sense. Also, we have to encode the connectors. So we need to encode the meaning of disjunctions and conjunctions and negations. Also, we made use of integrity constraints of the form, well, basically what cannot be included is that a formula in our knowledge base is false. But again, I'll give an example on the next slide, so this will probably make this a bit more clear. And finally, we also made use of minimized statements, because we always needed to minimize something. So in the case of the contingent inconsistency measure, we needed to minimize the number of atoms set to both. In case of the forgetting-based inconsistency measure, we wanted to minimize the number of forgotten atom occurrences. And in the case of the hitting set inconsistency measure, we aim to minimize the number of elements in the hitting set. All right, so let's look at an example. So I picked out the contingent inconsistency measure for this. I do not want to present all encodings of all measures, because I think I don't have enough time for that. But if you're interested, you can, of course, take a look at the paper. So we start with the unique atom evaluation. So with respect to an atom X, we define the following. So essentially what this does, it just means that if an atom X is true, then it cannot be both or false at the same time. In ASP, of course, this means that well, if the ASP atom EXT is included in the answer set, then EXB and EXF cannot be included. And of course, it's the same way for the other two truth values. So if it's B, then it cannot be T and F, and if it's F, it cannot be B and T. All right, next, we needed to encode the connectors. Again, I don't want to show all connector encodings. I just picked out the conjunction operation for this. So on the right, you can see an overview of the true, or you can see the truth value, truth table of Priest's three-value logic with respect to the conjunction operation. And the first thing we see is that a conjunction can only be true if both conjuncts are true. So just like in classical logic. And we can encode this like this first row here. So if the conjunction of phi and psi is true, then phi must be true and psi must be true as well. So next, we can also see that that a conjunction is false as soon as one of the two conjuncts is false. So you can see this here, 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 and here. So if psi is false, then the conjunction is false, and if phi is false, then the conjunction is false, and if psi is false, then also the conjunction is false. And finally, the only truth value left is B. So the conjunction is both if it's not false and not true. All right, and we also need to add integrity constraints for all formulas in the knowledge base, for all elements of the knowledge base, because we want to end up with a knowledge base that's either where each formula is either true or both, but it cannot be false because we want to have a model. So we forbid these atoms from going into an answer set by using these constraints. And finally, we want to minimize the number of atoms which are assigned the truth value B. So we do it just like that. We use this minimize statement for this. All right, now I would like to present our results because like I said, we also performed an evaluation. The idea of our evaluation was to compare the empirical runtime of our ASP-based implementations with existing baseline implementations of the individual measures. Just a few words on our implementation. As a programming language, we use Java because we made use of some libraries provided by Tweety project. And as the ASP solver, we used Klingo version 5.4.0. Some more details, we used 4 different data sets, which we also compiled because there is no dedicated data set for inconsistency measurement. We set a timeout to either 2 or 5 minutes, depending on the difficulty of the data set. And the baseline implementations are naive or brute force implementations, and they're also provided by Tweety project. Also, something I want to say about that, we use these implementations because, to the best of our knowledge, there are no other implementations of inconsistency measures, or of these inconsistency measures at least. All right, so the first data set is a synthetic one. We created this using the syntactic random sampler, which is also provided by Tweety project. We created this data set in a way such that the knowledge bases are supposed to be rather simple. So some of them are really small with just 5 to 10 formulas and the signature only having like 3 elements. In total, we created 1,200 knowledge bases. And like I said, the timeout is 2 minutes, and each knowledge base has between 5 and 50 formulas per knowledge base. And the cardinality of the signatures lies between 3 and 20. So here are the results. So this is a cactus plot, which means for each algorithm, for each measure, we measure the runtimes, obviously, and then we sorted them from low to high. And this dotted line here is the timeout of 2 minutes. So if you, for example, look at this here, this is these are the results of the naive version of the forgetting-based inconsistency measure. And you can see here that, okay, some instances were solved quite quickly. However, over 1,100 instances couldn't be solved at all because there was a timeout. So what we see here is that clearly the ASP variants of the algorithms are can perform the task much faster than the naive versions. So these three here are the naive ones, and those three are the ASP ones. Also, if you compare them directly, yeah, it's very clear. So and also it's nice to see that the ASP based algorithms did not have any timeouts, although the naive ones actually had timeouts in several hundred cases. So next, we created a quite similar data set, also using the syntactic random sampler. However, this was supposed to pose a greater challenge than dataset A. Here we came up with 600 knowledge bases with between 25 and 150 formulas per knowledge base. And the cardinality of the signatures lies between 25 and 30. And again, we set the timeout to 2 minutes. Now you can see that you don't see anything about the naive implementations. That's because they timed out in every single instance. And also you can see that this data set did prove to be more difficult, because also the ASP version of the ASP implementation of the forgetting-based inconsistency measure did time out in over 200 cases. And also the hitting set one produced a couple of timeouts. The only one that's still going quite well is the contention inconsistency measure, which is probably because the ASP program that you, or the amount of rules you need to create for the contention measure are much fewer than for the other two measures. So you need many more rules to encode the other two measures. So this is probably why you get these timeouts here. Okay, next was dataset C. So we did not just want to work with synthetic data. We also wanted to take some kind of real world data. So for this one, we looked at set competitions and extracted some unset instances from them. So these knowledge bases are sometimes quite big. So the biggest one has over 10,000 variables and 34,000 clauses. So this is really huge. But I should also say that there are also smaller ones with just a few hundred variables and a few hundred clauses. So one special property of this data set is that the inconsistency values are always just 1 with respect to the contention and forgetting-based inconsistency measure, and either 1 or infinity for the hitting set inconsistency measure. So there are apparently sometimes some contradictory formulas. And yeah, we have 105 knowledge bases in total, and we set the timeout to 5 minutes because it's a bit more challenging. Now this looks a bit different, because here you can see that the naive and the ASP-based algorithms perform more similar. So for example, if you take a look at the contention measure, so it's the orange one here and the red one here. Yes, the ASP one did perform a bit better, but still it's like the results are quite similar. This is probably due to the fact that the naive implementations look at the smallest possible inconsistency measure, inconsistency values first. So they first look at the value 1. And this is probably why they were able to actually compute these values quite efficiently. So this was not the case in the previous 2 data sets. There, the inconsistency values were much higher, and you can definitely see a difference there. All right, now the final data set. I hope I still have time for this. I'll make it quick. This was also one of the real world data sets, and it was about abstract argumentation. So essentially, we extracted some knowledge bases from benchmark data of the international competition on computational models of argumentation. And one task in this competition is to find stable extensions. And we encoded the instances and the problems of finding such stable extensions via the approach from Besnard, I'm not quite sure how to pronounce them. And we also additionally added some constraints, which ensured basically that a certain fraction of arguments are included in the extension. And these constraints often lead to the knowledge base being inconsistent. Here we have 326 knowledge bases in total, and we set the timeout to 5 minutes again. Yeah, and here this is not too surprising, I guess. Again, the ASP-based algorithms perform a bit faster than their respective naive counterparts. But also we should note that there is a quite large fraction of the data set that none of the algorithms could solve within 5 minutes. So there are also definitely limits to the ASP-based algorithms. So now let me quickly conclude. So we introduced ASP-based algorithms for 3 different inconsistency measures. And we also evaluated this against a set of naive baseline algorithms regarding runtime performance. And we could show that our newly proposed algorithms perform clearly superior. As far as future work goes, of course, it might make sense to consider further inconsistency measures, maybe also some with higher complexity. And also basically the biggest criticism we got so far on this work is that our baseline is too weak and that our results aren't very surprising. So the development of a more efficient baseline algorithm or set of better algorithms might also be something that we should do for future work. So that's it from my side. Thank you for your attention, and I'm happy to answer any questions.